So we'll start talking about hash functions, and we'll start with the one that works for integers. So if you remember from an introduction to a hash function, it's basically a function that kind of transforms a key into an index. Now, I said back then that there is a simple step that is missing from this picture. And what that is that regardless of what the hash function does and what its output is, in order to make its output to be useful as an index into the buckets or into this array, we always have to make sure that index is between 0 and the number of buckets, exclusive, obviously. So for example, if there are 7 buckets, then that that index must be between 0 and 6, right? So what if the hash function actually outputs a number that is, let's say 10, right? Well, we'll have to wrap it around. So, and to do that, the most common way is to really use the modulo operator. So really, the bucket index is the hash, whatever the output of the hash of the key is, modulo number of buckets. So that's the simple but very crucial step that was missing in the previous picture. Now, a couple notes on that is the modulo operation is not exactly cheap. So oftentimes we want fast performance. Then, if we make the number of buckets to be power of 2, then we can actually very quickly do the modulo operation by doing an bitwise AND with the number of buckets minus 1. So that comes from the binary way of writing numbers. So if you remember that, this should make sense right away. So in practice, power of 2 is actually used quite common. And then another note is that now this modulo step is generally not considered part of the hash function. Okay, but in practice, we often do the two together and we call it hash. So, but just be aware, this step must be there regardless of whatever the hash function does. All right, moving on. Let's assume, so like I said, we will talk about hash function for integers. So let's assume the key is an integer and each of key is the hash function. So one of the simplest hash function can be just that. It just returns a constant, whatever the constant is. In this case, it's 1. It might, it could be 10, 100, whatever. It's just a simple hash function. Now, if we use this hash function, what kind of problem are we going to run into? Well, obviously, every single key is going to end up in the same bucket. In this case, bucket number 1. So every single insertion will result in a collision, except the first one. So this is a terrible, terrible, terrible hash function, right? We want to avoid collision. So kind of intuitively, even though this is an extreme example, we'll never do something like that, but it gives you the intuition of what's a good hash function. A good hash function is to distribute the keys evenly to all buckets, with the equal probabilities. So the whole goal is so that we can minimize collisions. Okay, so another kind of a hash function example is, at least for integers, is just the integer itself. And despite its simplicity, this is actually not a bad hash function, but that would depend on the occurrences of the integers, right? So if all the integers occurs with equal probability, then this is actually a very good hash function, right? Because it's already evenly distributed. And as a matter of fact, this is how Python hash its integers. So let me bring up the my IDE here. And basically here I have a list of numbers. And for each one of them, I just call the built-in hash function on them. So if you run it, I already have the output down here. And you can see that, 0 hash to 0, 1 hash to 1, and so on. And this 4, 5, 6, 7, 8, 9 hash to 4, 5, 6, 7, 8, 9. Now, this works up to a certain point. I think when it gets very close to 2 to the 64th power, it starts to wrap around. So, but anyway, so that's what Python hash integers. And now, one thing I do want to also point out at this point is that hash, what it actually does is it just calls that object's dunder hash functions. So integer actually defines a dunder hash method, and that basically just returns the integer itself. Now, what that implies is that we can override it for the user-defined types, so that we can have custom hash function for the types that we define. We'll get to that later. Now, integers are not always evenly distributed, though. For example, I come up with this. This is a can example. It's not real, but it kind of illustrates the problem. Let's assume that whenever we want to allocate a CWID, it's done by adding 10 to the previously allocated CWID. So if we, the last one that was allocated is this number, so ignore everything in front, it's going to stay the same. The last 2 digits is 49. So we start at 49. If we want a new one, we go to 59. We want a new one, we go to 69, 79, and so on and so forth. Now, if our hash table has 10 buckets, and then the using then the bucket indexes would be whatever the number is, modulo 10, modulo 10, modulo 10, modulo 10, and we end up with a bucket number. They're all 9s. So all of these numbers are hashed to the same bucket. So that's not good. That causes a lot of collisions. Now we can kind of mitigate this problem by having a prime number of buckets. It doesn't actually strictly have to be prime, but anyway, so let's stick with the prime number. So if we use let's say number 11, which is the prime number of buckets, then we modulo every single one of these CWID by 11. What we end up with is the bucket index are 4, 3, 2, and 1, and that's great. They are all distributed to different buckets, so it's good. Now, is prime number of buckets, is it a solution to a bad hash function though? Is it always a solution? We see that it's kind of a solution in this case. Is it always a solution? Well, it's not. So just think about the really horrible hash function we talked about earlier. This one, it just always return the number 1. So it doesn't matter what the number of bucket is, whether it's prime or not. All keys will end up going to the same bucket. So the prime number of buckets, it's not a fix-all kind of solution. Now, on the other hand, if a hash function is already distributed keys evenly, the number of buckets, whether it's prime or not, really cannot mess it up. The only way that it can mess things up is like the number of buckets is really, really tiny, like 1. Then it doesn't matter how good the hash function is, everything's going to end up in the same place. So the kind of the conclusion is having a good hash function is very, very, very important. And you'll see me repeat this throughout the rest of the lectures on hash table. And also, one observation is the hash function is kind of a property of the key, right? Usually, if it's an integer, whoever wrote the integer class determines how it's hashed. If it's a string, which we'll talk about in a bit, whoever wrote the string class determines how to hash a string. So that's hash function is managed in most cases by the creator of the key. Okay, now the number of buckets, on the other hand, is the property of the hash table. So it's managed by the creator of the hash table. In this case, because we're studying hash table, it's us. So And the observation was that having a prime number of buckets is good. It doesn't hurt. It actually helps in certain scenarios. And actually, when we get to our implementations, we will use prime number buckets just to be consistent with what's in the readings. But it's actually also required for certain type of collision resolution schemes. But just be aware that it's not a solution to everything. It has limited values.